Imagine a bowling ball placed on a trampoline. The ball creates a dip, a curvature in the trampoline's surface. This is a simple analogy for how Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. In general relativity, gravity is not a force acting over distances, but a manifestation of the geometry of space-time itself. Massive objects like stars and planets warp the fabric of space-time, much like the bowling ball on the trampoline. This curvature dictates how objects move in the universe. Imagine a marble rolling on the trampoline. It will follow a curved path around the bowling ball, not because of any force pulling it, but because the trampoline itself is curved. This is how general relativity explains the motion of planets around stars. They are not pulled by a mysterious force but rather follow the curves in space-time created by the star's mass. General relativity has been incredibly successful in explaining a wide range of phenomena, from the bending of starlight around massive objects to the existence of black holes. Einstein's vision of gravity as geometry is one of the most profound and elegant theories in physics. It paints a picture of a universe where gravity is not a force, but an intrinsic property of the fabric of reality itself. While general relativity describes the universe on the grand scale, quantum mechanics reigns supreme in the microscopic realm of atoms and subatomic particles. Quantum mechanics offers a very different picture of forces. In the quantum world, forces are not smooth, continuous actions but rather arise from the exchange of discrete packets of energy called quanta. These quanta are carried by fundamental particles called bosons. For example, the electromagnetic force responsible for light and electricity is carried by photons. Similarly, the weak and strong nuclear forces which govern the interactions within atomic nuclei are mediated by W and Z bosons and gluons respectively. If other forces operate through the exchange of particles, it seems natural to ask if gravity does the same. This hypothetical particle, responsible for mediating the gravitational force, is called the graviton. The graviton is thought to be massless, like the photon, which explains why gravity has an infinite range. However, unlike the photon, which has been experimentally confirmed, the graviton remains elusive. Although both general relativity and quantum mechanics are incredibly successful in their respective domains, they paint very different pictures of reality. This becomes glaringly apparent when we try to understand extreme environments where both gravity and quantum effects are significant, such as the center of black holes or the very first moments of the universe. One major point of friction is the concept of quantization. In quantum mechanics, energy, momentum, and other physical quantities are quantized, meaning they can only exist in discrete values. However, general relativity treats space-time as a smooth, continuous fabric. This clash between the discrete and the continuous lies at the heart of the conflict between general relativity and quantum mechanics. Another challenge is the sheer weakness of gravity compared to the other forces. While the other forces are strong enough to be easily observed at the quantum level, gravity is so weak that its quantum effects are thought to be only noticeable at incredibly high energies, far beyond the reach of current experiments. This makes it incredibly difficult to test any theory that attempts to unify gravity with quantum mechanics. Despite these challenges, physicists have made significant progress in developing theories that attempt to reconcile general relativity and quantum mechanics. Two of the most promising candidates are string theory and loop quantum gravity. These theories offer radically different approaches to the problem of quantum gravity, but share the common goal of unifying our understanding of the universe at its most fundamental level. Imagine the universe not as a collection of point-like particles but as a cosmic symphony of tiny, vibrating strings. This is the fundamental idea behind string theory. In this elegant framework, the different particles and forces we observe are simply different vibrational modes of these fundamental strings. String theory proposes that these strings are incredibly small, far smaller than anything we can currently observe. Just as different vibrations of a violin string produce different musical notes, different vibrations of these fundamental strings give rise to the different particles and forces we see in the universe. One of the most appealing aspects of string theory is that it naturally incorporates gravity. Unlike other forces which require additional theoretical frameworks to be incorporated into a quantum description, gravity emerges naturally from the mathematics of vibrating strings. This has led some physicists to believe that string theory may hold the key to unifying all the forces of nature, into a single, elegant framework. However, string theory is not without its challenges. One major obstacle is the sheer complexity of the theory. String theory requires extra spatial dimensions beyond the three we experience, and the mathematics involved is notoriously difficult. Furthermore, string theory has yet to make any testable predictions that could definitively confirm or refute its validity. Section 5. Loop quantum gravity, weaving space and time from tiny loops. Unlike string theory, which starts with the idea of strings and attempts to derive space-time, loop quantum gravity, or LQG, takes a more bottom-up approach. LQG begins with the fabric of spacetime itself and attempts to quantize it directly using the language of quantum mechanics. In LQG, space is not smooth and continuous but is woven from tiny, indivisible loops of gravitational energy. These loops, called spin networks, are the fundamental building blocks of spacetime itself. The size of these loops is incredibly small, on the order of the Planck length, which is about 10 to the power of minus 35 meters. LQG predicts that spacetime has a granular structure at this incredibly tiny scale. This is analogous to how a seemingly smooth piece of fabric, when viewed up close, is actually made up of individual threads. Just as you cannot divide a thread in half and still have a thread, LQG suggests that spacetime itself cannot be divided indefinitely. One of the most intriguing implications of LQG is that it suggests a possible resolution to the singularity problem in general relativity. Singularities, such as those at the center of black holes, are points where the curvature of spacetime becomes infinite, and the laws of physics break down. LQG suggests that the discrete nature of spacetime prevents these infinities from arising, potentially resolving one of the most perplexing problems in modern physics. Section 6. Emergent gravity. Could spacetime be born from something deeper? While string theory and loop quantum gravity represent two of the most prominent approaches to unifying gravity with quantum mechanics, they are not the only contenders. Another intriguing possibility is that gravity is not a fundamental force at all but rather an emergent phenomenon. Just as the temperature of a system is not a fundamental property of individual molecules but rather emerges from their collective behavior, some physicists believe that gravity may emerge from a deeper, more fundamental level of reality. In this view, spacetime itself would not be fundamental but would emerge from the collective behavior of microscopic constituents. One promising approach to emergent gravity is the holographic principle. This principle, inspired by the behavior of black holes, suggests that the information content of a region of space is encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. If the holographic principle holds true, it implies that gravity, which governs the geometry of spacetime, may be a manifestation of the entanglement, or interconnectedness, of these microscopic degrees of freedom. This radical idea suggests that spacetime itself may be a kind of illusion, emerging from a deeper level of reality where gravity is not a fundamental force. Section 7. The meaning of fundamental, a philosophical labyrinth. The quest to understand the nature of gravity leads us to a fundamental question. What does it mean for something to be fundamental? In physics, we often strive to find the most basic, indivisible building blocks of reality. But what if our notion of fundamental is itself flawed? Is it possible that what we consider fundamental depends on our perspective and the scale at which we are observing the universe? Perhaps what appears fundamental at one level of reality emerges from the collective behavior of something deeper still. The search for a quantum theory of gravity forces us to confront these profound philosophical questions. It challenges our assumptions about the nature of space, time, and reality itself. As we delve deeper into the quantum realm, we may find that our classical intuitions no longer apply. Section 8. The quest continues. Unraveling the enigma of gravity. Despite decades of research, the true nature of gravity remains one of the biggest mysteries in modern physics. While general relativity and quantum mechanics have been incredibly successful in their respective domains, a complete theory of quantum gravity remains elusive. The challenges are immense. The extreme weakness of gravity makes it incredibly difficult to test any theory that attempts to unify it with the other forces. Furthermore, the clash between the continuous nature of spacetime and general relativity and the discrete nature of quantum mechanics presents a formidable theoretical hurdle. Yet, physicists remain undeterred. The quest to unify gravity with quantum mechanics is not merely an academic exercise, it is driven by the deep-seated human desire to understand the fundamental nature of the universe we inhabit. New theoretical frameworks such as string theory, loop quantum gravity and emergent gravity offer tantalizing glimpses into a realm where gravity and quantum mechanics coexist harmoniously. Advanced experimental techniques are constantly pushing the boundaries of what we can observe, searching for subtle clues that could guide us towards a more complete understanding of gravity. Section 9. Conclusion: a universe of mysteries yet to be solved. The journey to unravel the enigma of gravity has been long and arduous, marked by both profound insights and frustrating dead ends. While we have made remarkable progress in understanding the universe, gravity continues to pose a formidable challenge, a constant reminder of the limits of our current knowledge. Whether gravity is ultimately described as a curvature in space-time, a quantum force mediated by gravitons, or an emergent phenomenon arising from a deeper level of reality, the pursuit of a unified theory of physics promises to revolutionize our understanding of the cosmos. As we continue to explore the universe at its most fundamental levels, we can be certain that new discoveries await, discoveries that may challenge our deepest intuitions and reshape our understanding of the nature of reality itself. The quest to understand gravity is not just a search for a single equation, it is a journey into the very heart of what it means to exist. It is a journey that will continue to inspire and challenge us for generations to come,